braids, we can avoid gates by doing certain special measurements. Teleportation. But still, before going into teleportation, I wanted to explain the gate model. So this is what we do. We braid them, and so for example, if it's good to have two pictures in mind always. So one is sort of the top-down picture, and then the other is the picture of you think of it like a horizontal picture of the braiding diagram. So top-down, when you switch A and B, this is what happens to the fusion diagram. So I pulled A in front of B. This is supposed to go in front of that. And so the direction matters. If I did it in this direction, then that would go under. And now these states are still orthonormal. Like all pop. If you look at fusion diagrams that look like this, and have different labels, those are all orthonormal. But the thing that we do is we change basis back into the original basis, and that'll be a non-trivial operation. So this state is some linear combination of states in this basis. Okay. Right. So here, what can you say? I can say that A, B, C, that ket is equal to R, A, B, C times B, A, C. So this twisted diagram is equal to some phase times this untwisted diagram. Where R, A, B, C, it's a complex number of magnitude 1. And it's part of the specification of the model. So when somebody tells you Fibonacci model, or Ising model, they gotta tell you what all these numbers are. Okay. Yes, for bosons it's 1. For fermions it's -1.
So those phases act as gates.
Well, this isn't quite interesting enough, right? So not yet, because this is only we can't get superpositions. This is all we had, so there's got to be more. Yeah. Okay, so let me skip that. Let me show you the model then. This is a Fibonacci model, I think in all the detail. So tau is the golden ratio. It's like 1 point something. 1.6, 1.8, I don't know.
1.68.
1.68. Right. So tau is the golden ratio, and these are. Let's see what I'll show you. What's called the F move shows you how to change from the basis where you first merge these two, and then you merge this into where you first merge these two, and then you merge this. So I'm switching the order in which I merge. So they're both orthonormal bases, but there's some interesting relationship between. And so this is the F move here for the Fibonacci model. If the first two merge to 0, then that's the same here as 1 over tau times 0 plus 1 over root tau times 1. So that's confusing. Yeah. So think of it this way. So here I have 3 particles, and their total charge is 1.
Okay.
That means I have a qubit. So this could be a 0, or this could be a 1. Okay, so there's 1 degree of freedom there. So these are the 2 possible basis states if I merge them in this order. First A, B, and then C. These are the 2 possible basis states if I merge them in this order. First B, C, and then A. So what this tells us is this tells us how this basis relates to that basis. It gives us the change of basis matrix between these 2 basis states and those 2 basis states.
Okay, but where do these tau factors come from?
Tau is just a number. It really is 1.6.
No, wait. If we
Where
grab
did
the
you get them from?
The tau comes from Fibonacci.
Oh, Fibonacci. Yeah.
It's given to you, yeah.
Yeah, but how did you get it in this example? Like,
Oh.
how did you
I
get
think
the factor?
Fibonacci, yeah.
Like you have to Google it.
No, I mean like, are those the coefficients for that extension?
Right, so you can't put any number there. So a few things. First of all, there are constraints. So first of all, this is an orthonormal basis, this is an orthonormal basis. Therefore, this 2 by 2 matrix, 1 over tau, 1 over root tau, 1 over root tau, minus 1 over tau, that 2 by 2 matrix had better be a unitary matrix because it changes from one orthonormal basis to another orthonormal basis. That's one constraint, it's a simple constraint, but still there's more constraints. So the other constraints are, do I have it? Here.